right, guys, today I'm going to cover the beginning of chapter 5, so 5.1 compounds and molecules. So a couple of things just for review. Elements are made up of individual atoms. They cannot be broken down into simpler substances because they lose their properties. These elements are listed on the periodic table, and they are the building blocks of all matter. Also, we have mixtures. These are just different substances that are placed together. These substances can keep their individual properties, and they're usually easily separated like sand and gravel. Or maybe a salad that you can pick out like carrots if you don't like carrots. So compounds are two or more elements bonded together. That is a compound. So some compounds that you might know would be like sodium chloride that we've talked about. That's actually table salt. That's a sodium, which is Na, plus your chlorine, which is Cl. Okay. They have properties different from the original element. So like we talked about before, sodium is explosive in water. Chlorine is really caustic and hazardous. We use it for a cleaning agent. But together they make delicious table salt. And our bodies actually need that, right? So they lose those properties of the original element and they combine to make their own new properties. It has a chemical formula. It is not easily separated. And so, of course, then it has new properties like I talked about. So atoms are to elements as molecules are to compounds. So then we get to the idea of a chemical formula. Every compound has to have a chemical formula because this tells you how many atoms of each element are actually in the compound, but not its structure. So for example, if we're looking at H2O, I know that there's 2 hydrogen and 1 oxygen based on the H2O. If you're looking at the bottom left-hand corner of the slide, right? But it does not tell me how it is structured or organized, but it does tell me how many of each element I have. So this is like its own fingerprint, so to speak, for that chemical. Okay. Same thing with sugar, just a chemical formula for sugar there. C12H22O11. Bonus points if you know which type of sugar. It's actually glucose, for those of you photosynthesis lovers. And we'll talk about photosynthesis again coming up. Okay. So what we have is this idea of a chemical formula. Well, how can we use the chemical formula? Well, we can actually use it in the molecular or empirical formula. Okay. So this is literally the bare bones formula is the empirical formula. So it's the formula with the smallest whole number mole ratio of the element. So there are several chemicals that could have the same empirical formula, but different molecular formulas, okay? So they may or may not be the same as the molecular formula. So keeping that in mind, there might be several actual elements or several actual compounds that have the empirical formula, like CO2. That would be the bare bones, but there might be multiple chemical formulas that are their molecular formula that are bigger than that. So an example that I use here is hydrogen peroxide, right? That bubbly stuff that you put when you get a scrape, or maybe you skin the side of your face or something like that. So its empirical formula, the bare bones formula, is actually just what atoms are in it. So I know its empirical formula is it has at least 1 hydrogen, it has at least 1 oxygen. But when I look at that specific chemical formula that we call the molecular formula for hydrogen peroxide, it's actually H2O2, meaning for hydrogen peroxide, I know I have 2 hydrogen and 2 oxygen that make up its fingerprint. So then we get the idea of these chemical bonds. Okay. So bonds are actually the attractive forces that hold together atoms. And so this is where we get the idea of opposites attract. So I will have a negative ion that's attracted to a positive ion, right? So a metal attracted to a non-metal. All right. and vice versa. If they're the same ion, the same charge of ion, they will not be attracted to each other. Okay, so I can't have two negatives that want to come together. They'll actually want to they'll force themselves apart. So it's always opposites attract when it comes to chemical bonds. So then we get to the idea of the bond length, right? It's just the distance between the nuclei of two bonded atoms. So the distance between the nucleus. Okay, and based on the distance of that bond length from nucleus to nucleus, usually that makes the atom either stronger or weaker. The stronger bonds are usually shorter bonds, whereas longer bonds are usually weaker. Okay. And then we get to the difference in bond angle. It literally tells me how the atoms are oriented within that compound. Okay, so it's all based on the atom orientation with different atoms. So here you can see in the picture the water molecule, and the atoms are arranged towards one side. Notice the positive ions of hydrogen are attached and bonded to the negative ion of oxygen, but they are attached at 104.5 degree angle. Okay, so that's my orientation. If you turn it upside down, it kind of looks like Mickey Mouse ears, right? So that's its orientation. It's based on the chemical bonds, so what atoms are bonded together, the bond length, meaning how short or long is that bond, and the bond angle, so the orientation of the atoms around each other. Okay. So then we get to the different models. There's really three different models that I talk about. A being the ball and stick model, which you can see that to the right-hand side there. Okay, this also, there is a space filling, B, which looks straight down. The space filling one, it literally fills up all the space, kind of looks like a caterpillar. And then you get the structural formula, which is C. That's my favorite one. It's down to the bottom right there, the structural formula. Okay, so the structural formulas actually show the structure of the compound. So you can actually notice the difference in the chemical symbols and how they're oriented around each other. Okay, this actually helps you see a compound structure. Okay. So now we get to the different structure and properties. So we have really just a network of atoms and how they're combined together. Okay. So if we're looking, right, we can look at different solids. In this case, silicon dioxide, right, SiO2. And we can see the angles. They all have 109.5 degree angles. And they have very short bonds, it looks like. And so all angles are the same throughout. So that makes this solid substance literally extremely strong, extremely rigid, and it has a very high melting point, which means I would have to heat this substance up to very high temperatures to get it to even start to break down. So then we get to the point where what is an ionic bond, right? So ionic bond is your positive with your negative. Okay, so your positive ion gets attracted to your negative ion, which means your metal gets attracted to your non-metal. And what happens is the metal actually donates a valence electron to the non-metal. Remember when I talked about ions, the metals that form your cation it has too many, it wants to get rid of some, at least one. And your nonmetals, which form your anions, they want to get to 8, right? They want to be like the noble gases. So they need those electrons. And so the metal says, hey, I have 1 extra, you can take mine. Or I have 2 extra, you can take mine. And that forms a bond. So some examples of an ionic bond for these molecules would be magnesium chloride. Notice that magnesium is a metal on the periodic table and chlorine is a non-metal on the periodic table. Same thing with your table salt, sodium chloride. Sodium is a metal, chlorine is a non-metal. So those are examples of ionic bonds, okay? So then we get to looking at exactly the structure, right? How does this positive ion get attracted to the negative ion, and what does it look like if I were to look at it? And so what I see here is a very cuboidal structure, which means it's strong, it's rigid, and has an extremely high melting point. Okay. Then we get on to covalent bonds. Which is your nonmetal plus your nonmetal. That's a negative. That's your negative ion attached to another negative ion. So what happens is the valence electrons are actually shared between the two atoms. So here's some examples there. You got nitrogen dioxide, right? Dihydrogen monoxide, which is actually just water. And so you have nonmetal bonded to nonmetal. And so that's your covalent bonds. All right, I am going to stop there. If you have any questions, please let me know. Just send me an email.